we are pleased, our pleasure to have Professor Feng GAO with us today. Professor Feng GAO is a full professor and the head of optoelectronics unit at Linkoping University in Sweden since 2020. He has been appointed as a Willingsburg Scholar since 2024. His group focuses on emerging semiconductors for the next generation optoelectronic devices. He obtained his PhD degree in 2021 from the University of Cambridge, MS, BS degree from Nanjing University. He received from the European Research Council an ERC Consolidator grant and the ERC Starting Grant 2016. He became the Sweden Foundation for Strategic Research Future Unit Leaders in 2019 and the Willingsburg Academy Fellow in 2017. He received the Tech Erlander Prize in Physics 2020 and the Gunvor Gustafsson Prize in Physics 2025, both awarded by the Royal Sweden Academy of Sciences. Let's welcome Professor Dean. We have Dean, right? We have our Dean to give a remarks for the speech. Yeah.
So it's my pleasure to also introduce the speaker, but I also have the added responsibility of telling you a little bit about this lecture series. And so first, welcome to all of our guests, especially our speaker today. And this is one of these interesting topics, both because it covers sustainability, but also because optoelectronics and optoelectronic devices are such interesting technologies. And so I think we're all looking forward to hearing your presentation today. So this is part of the William Mong Distinguished Lecture Series, which was started in 1991. And this has been a series that's really trying to bring top scholars from around the world to HKU to tell us about what's going on outside of our borders. It's named after Dr. William Mong, who was a founder of the Ching group, and it was not only was he a very successful entrepreneur and grew a very large company, but he also was very philanthropic, and his family also continued that philanthropy. And so it's a pleasure that we get to continue his legacy through talks like this and learn more about what's going on. So Professor Feng GAO is a distinguished figure in the field of optoelectronics and a leading professor at Linkoping University. By the way, I had to look up how to pronounce that. It's not quite as obvious as it sounds, as it looks. So since 2020, he's been at the forefront of exploring novel semiconductors and looking at optoelectronic devices. He's won many awards, and in the interest of not taking all his time, I'm not going to list them all. But today's talk, as you can see, is sustainable development of next generation solar cells and LEDs. If you pardon the pun, it should be an enlightening talk. Should illuminate all of our imaginations. The work looks at energy efficiency, environmental sustainability, low cost, green solvent-based technologies, all of which I think are very much of interest in today's world, given the challenges we're facing in climate challenges, and at the same time as we try to move the technology forward. Moving the technology forward, I think, is for most of us engineers is where we spend most of our time thinking about how do we advance the technology, but doing it in the right way is, it takes, a different kind of dedication. And so we're very much looking forward to hearing about this. And so without any further ado, let me turn the floor over to our speaker, and very much looking forward to hearing what Professor GAO is going to tell us. And, I have one more responsibility, which I always forget. They told us that we always have to give out the award in anticipation of a great talk instead of as a reward for a great talk. So we got to smile.
Very much, Tim, and also Professor Chow for the invitation and also the kind of introduction. It's really my great pleasure to visit Hong Kong U and to speak at this distinguished lecture series. And today I will talk to you about next generation solar cells and LEDs. I will focus on the sustainability aspects of this solar cells and LEDs. To be more specific, because there are many different solar cells and LEDs, I wouldn't kind of be able to cover all of these different materials and devices. I will focus on solar cells and LEDs based on material which is called metal halide perovskites. Some background, some motivation. So why do we need the next generation solar cells? And nowadays, many areas and many countries have ambition for carbon neutral by 2050 or 2060. This is kind of this is not a kind of general public article. It's really a serious research article. This kind of predicts how the energy share will change in the next few decades. And as you can see here, represented by this pink area, this is solar PV. So now we are 2025. So solar PV is still the contribution is not very high yet. But by 2050 or even 2060, the solar PV contribution will be more than half of all of the energy contribution. And nowadays, solars are mainly dominated by silicon solar cells. And then why do we need a next generation? Go beyond the silicon. There are several different reasons for that. First of all, if we tandem silicon with some other PV technologies, we can gain much higher energy, a much higher power conversion efficiency. And this is a little bit kind of busy slide, but I can guide you through it, especially some important figures. So this is the kind of the Shockley equator limit for single junction solar cell, and the limit is about 33% for single junction solar cell. But in practice, there are many kind of limitations, and this is a practical limit, is slightly above 25. And if you tandem two materials together to make a tandem solar cell, and the limit can go to around 45%. So you gain quite a lot of efficiency by going from the single junction to the tandem solar cells, tandem junction. And this is a paper was published in 2017. At that point, we have a lot of different tandem solar cells. But nowadays, so you can see this is a tandem, updated tandem solar cells based on silicon and perovskites. Now it's already kind of over the limit of the single junction solar cell. So you can see that by tandem silicon PVs with emerging PVs, we can really improve the power conversion efficiency. This is one of the reasons. using the same areas, then we can generate more power. So that's the reason why we need next generation solar cells. There are some other reasons. This is the silicon kind of which is black, right, and rigid. But for the new generation of solar cells, they can be made into different colors. They can be made into semi-transparent. This is kind of especially attractive for our urban settings. We need the energy. We also need a kind of beautiful panels. And yeah, as I mentioned just now, the silicon they are rigid. But for the next generation solar cells, they can be flexible, so that we can put them on some curved areas quite easily. And that's hardly possible for silicon solar cells. So because of these reasons, we can have more application scenarios compared with silicon. So it's the wrong direction. And there's some other reasons. For example, this is a parameter which is very important for solar cells, which is called energy payback time. That means when we produce any solar cells, we need to invest the energy during the production process. And when you after the production, you start to use those solar cells, and then you need to spend some time to gain back the energy you invest in the production. And this is called energy payback time. How much time you need to really gain back all of the energy during your production. For silicon, it's somewhere around 2 and 2.5 years. But for our emerging solar cells, for example, organic solar cells and perovskite solar cells, they are quite often less than half a year. So this is another reason why we are motivated to develop a next generation solar cells for this shorter energy payback time. The kind of perovskites, some of you guys might be familiar with the material. A very, very, very interesting semiconductor nowadays are used for many optoelectronic devices, solar cells, LEDs, lasers, and X-ray detectors. And this is kind of a composition. Chemical structure of perovskites is composed of organic cations. It can be also inorganic, and metal cations, lead and tin, and highlighted anions. And this material can be very easily processed through solution or use some low temperature evaporation. And especially if you consider solution processing, you put the materials together and you're using together in some solution. It's kind of dirty chemistry, right? And then you spin coating in the lab, or you do some printing, hopefully potentially for the large scale applications. And this is kind of very relative dirty chemistry results in very high quality semiconductors. That's kind of the magic property of this material. There are kind of many discussions of why this material is so good, but I would like to highlight one point which I really think is important for this material, which is the defect tolerance. For the inorganic semiconductor, conventional inorganic semiconductor, the whole industry spent a lot of efforts to take care of the traps, defects, because kind of gallium arsenide, they have deep traps. That's the reason the industry needs really to spend so many efforts to take care of them. For perovskites, the interesting thing is they also have kind of defect states. But the defect states, they are either within the CB or conducting band or valence band, or they are very close to the CB and the VB. That's the reason why they are called shallow traps. So you don't need to spend too many efforts. You try to control the crystallization process, or you add some organic molecules to precipitate these defects, so that you can relatively easily take care of these shallow traps. That's kind of one of the reasons why the perovskites, in spite of this easy processing from solution, they can have very high quality properties and make them very promising for many different optoelectronic devices. If we look at the kind of efficiency development of perovskite solar cells, it's very quick. The first perovskite solar cell was published in 2009. Now it's 2025. The efficiency went from around 3% to nowadays more than 26%. In the PV history, no other materials can have reached such a kind of quick development in terms of the efficiency. And certainly for practical applications, we need to care about the efficiency, but we also need to care about the stability. And there are quite a lot of efforts in the community to improve the stability, because this has been considered an issue for perovskites, which are ionic semiconductor with some issues with the stability. And during the past several years, we have also made some contributions in this area, try to improve the stability. I will give you two examples. One is a paper we published together with Professor Harrison's group at Oxford quite some years ago. In that case, we added some ionic liquids into the precursor. And in the end, we found that these ionic liquids can really minimize ion migration within the perovskite. That's the reason why you can really improve the stability quite a lot by adding these ionic liquids. And in this case, we are kind of providing continuous illumination to the solar cells. But later on, by collaborating with another group from Seoul University, led by Professor Liao Wen and Liu Fang, and we realized that perovskite solar cells under continuous illumination, so the stability is very much different from the situation where the solar cells are under recycled illumination. Because in practical applications, we have daytime and we have nighttime. It's kind of a cycle illumination. And if without kind of seeing these results, we might be assuming and the cycle recycling, the stability would be better compared with the continuous illumination, because during the daytime, okay, the solar cells, they are working very hard, but during the nighttime, the solar cells can rest. And during rest, then maybe they can even, there are many discussions about self-healing, they can recover. But in reality, if we have a look at the stability, it's not the case. This red curve is a cycle illumination, and this blue curve is a continuous illumination. And you can see, actually, the solar cells, they degrade even quicker and the cycle illumination compared with the continuous illumination. We spent quite some time to understand the mechanism behind that, and the reasons we figure out are because the thermal expansion coefficient of the perovskite, the active material, and the thermal expansion coefficient of the substrate, they are very much different. And then during the cycle illumination, and because of the light and also temperature difference, you create a lot of stress between the interface of the perovskite and the substrate, and also cause a lot of defects and traps. That's the reason why actually during the cycle recycling, illumination is even the stability is even worse. This is very much different compared with I would intuitively imagine. And later on, we figure out some practical ways to solve this issue, and more specifically, Professor Liao Wen and Liu Fang's group, they designed a molecular which is special in terms of the fact that this molecular has phase transition at the relatively low temperature, around 40 degrees, and then during the cycle illumination, it can in situ adjust the strain, the strain and stress between the perovskite and the substrate, and then we happily solve this problem. But this is not the focus today, so I will move forward. Kind of because of the enhanced efficiency and also enhanced stability, there are nowadays a lot of commercial efforts, activities trying to put the perovskite solar cells into market. Certainly, this is not a completed list. I'm sure there are new companies almost every month. I wouldn't say every week, but at least every month all over the world. But concerns remain, especially for perovskites. The high efficiency ones, we need to include lead. Lead is toxic, and if the solar panels they are broken, maybe the lead will result in our photo chain, and in the end, they will result in our human bodies and cause health issues. Because of these concerns, there are also quite some efforts in the community trying to solve these issues. There are several types of ideas. One is for lead capturing, and the idea is, okay, if your solar panels are broken, but we have some some materials, in this case, is some polymers, which can coordinate with lead very strongly. So after the solar panels are broken, unfortunately, by this lead, they can capture by these polymers, so then they don't go into our soil. Another idea is to recycle the lead. And in this case, as you can see here, it's lead iodide. It's the yellow powder. And we really kind of, in this case, we really focus on the recycling of lead, and then we discard other components in the perovskite solar cells. I totally agree, lead recycling is very important, but is it sufficient? You wanted to answer this question, so let's have a look at the kind of mature silicon solar cells. Let's learn from this history of silicon solar cells. The mass installation of silicon solar cells started around in 1999, that kind of 1 gigawatt installation. And after more than 10 years, and people realize, okay, the silicon solar cells, they are starting to degrade. We have some problems to take care of the waste silicon panels. And then in 2012, the EU have this WEEE directive. This WEEE, that means waste of electrical and electronic equipment. This WEEE directive basically means that the producers, they are responsible for the recycling. And 4 years later, in 2016, around 0.17% of the waste solar panels were recycled. And 2 years later, 2018, the number increased to around more than 17%. This looks very encouraging, right? Without this WEEE directive, then the PV producers, they are certainly not motivated to do any recycling. Landfill is the most kind of economical way, right? They don't need to spend too much time on that. And now they are required to have the recycling. Can you guys guess how the PV companies, they are kind of take care of the recycling? I give you 10 seconds. I give some water. You can think about it. I give you the result. This is how the PV panels are recycled. Basically, they are kind of ground into catalysts as fillers in building concrete. So consider we spend so much energy, so many efforts to develop this high quality silicon, and after they degrade, we just use them as building concrete. So I wouldn't call it recycle. Instead, I would call it downcycle. But there's a reason for that, because in practice there are no low cost, high value recycling approach for silicon panels. That's the reason we have now the community is doing this. Now there are kind of many kind of calls from different agencies trying to encourage the development of low cost, high value recycling of silicon panels. So by looking at the history of silicon development, the answer I asked in the previous slide is certainly later recycling is important, but it's not sufficient. So I would like to highlight the sustainable development of emerging PVs, no matter whether it's perovskites or some other materials. They require the investigation of recycling before we put them into market. If we don't do it now we will face the same challenges, same problems in 10 or 20 years later as we face for silicon solar cells nowadays. And this is also kind of the reason why the perovskite community, and we say that we need to go from this linear economy to the circular economy. And then we start to think, okay, what's the optimal recycling approach for perovskite PVs? Our understanding is we need to take three parameters into consideration, from the technology point of view, from the economic point of view, and also from the society point of view. From the technology point of view, so I would like to highlight the feasibility. By feasibility, I mean this recycling technology should have a high recovering yield, and also should be scalable, and also should be reliable. And from the economic point of view, is the processing cost should be low, because if the processing cost is very high, the PV producers, they are not motivated to that, right? And they also, we need to recycle them into high value product, not the kind of not downcycle them. And from the site point of view, we care about sustainability. Certainly, we don't want our recycling process to create additional energy, kind of negative environmental impacts, and we don't want to create any health risks for the workers or for neighbors. By putting these three considerations together, the ideal solution in our mind would be a reliable, high-value recycled product with pollution-free recycling approach. This was our ambition when we started this project, and this is our kind of vision. So we have the solar farm that produces the energy to the power company. The power company that supply the energy to the users. And then after some years, maybe 10 years, so hopefully even 20 years for perovskite solar panels, and in the end they were degraded. After the degradation, we know kind of the perovskite solar cells have many different layers, and we hope that we can recover each and every layer from the covering glass to the transport layers, to the perovskites, and then also to the substrate. And then we can use the recycled component to make new panels. And hopefully, the new panels are as efficient and as stable as the ones made from virgin materials. This is our ambition and vision. But when we started to work on that, I realized it wasn't easy. Like some of the parts are not so difficult. For example, the covering glass that wasn't difficult. But for example, for the whole transport material, in our case, is the spiral augmentate. It's not easy. The reason is the spiral augmentate is by itself, it's not a very good charge transport material. The energetic labels are not really aligned with perovskites. The charge transport is really poor. In order to make it into a good charge transport material, you need to duplicate this material. And conventionally, this conventional method has been in literature for many years. The conventional doping way is you add some lithium salt and you also add some TBP to the spiral, and then you expose your film to the air for maybe 1 day or 2 days. For the reaction to happen, for the oxidation to happen. And this is a very complicated kind of chemistry process. And in the end, it results a lot of byproducts. Some of the byproducts we know, I listed here. Some of the byproducts we don't even know. So let's make the recycling with the spiral really challenging. And very fortunately, 3 years ago, we developed something which we call ion-modulated radical doping. And then in this case, we make it very clean. We just added 2 materials. We know kind of this is not 2 materials. So we added 2 spiral. One is a spiral radical, and the other one is organic salt. And then because the kind of doping process is through the radicals and modulated by this organic salts, we don't need to put the mixture in the air for oxidation. We mix them together, and we can use it directly. And so this is kind of a clean process. There's no byproduct. It's also very stable. So now with this clean doping strategy, then we can recycle spiral. We use the ethanol acetate as the solvent, and we use the allyl salt as a reductant, and they use the ethanol as anti-solvent. We can recycle spiral with a very high recycling ratio, around slightly more than 97%. So far so good. And the next challenge is recycling of perovskites. I would like to emphasize. So when we recycle the perovskites, we really keep these 3 parameters in mind: economy, technology, and also society. And these 3 requirements really kind of make our recycling very challenging from the scientific point of view. And we spent quite a lot of efforts trying to figure out how to do that. And in the end, so we were happy we were able to do that. I will show you. So the the solvent we use is water. I think this is kind of the greenest solvent we can think of, and also very low cost. And in the water we add some some compounds. We have sodium iodide and we have sodium acetate, and we also have hypophosphorus acid. And this is also a very low cost material. And I will show you a video how we do that. Just by using this water-based solution, we put the degraded perovskite film into the solution, and you can see the perovskite films are dissolved. And this is relatively high temperature, 90 degrees. And then by cooling down to room temperature, and we can recover high-quality perovskites from this water solution, this kind of black powders. And then we can use we can collect the black powders and then dissolve them into solvent to make a new perovskite solar panels, solar cells. And then we can even repeat this process for many times. So we initially we using the fresh materials to make a perovskite solar cell, and then we degrade them. And after degradation, we recover all of the materials. And we use the recovered material to make a new perovskite solar cell, and we recycle this several times. And in this case, we demonstrated the results for 5 times recycling. And as you can see here, the efficiency for the solar cells made from the virgin materials, if you look at the distribution, kind of its average values are very similar compared with the device made from the recycled materials after 5 recycling. And the distribution of the efficiency is even kind of narrower after 5 times recycling. That's because each time of the recycling, actually, that's kind of a recrystallization process for our perovskites. It's also a purification process to make a kind of better quality of the perovskite. And our recycling is not only a recycling; it's also a repair process. Using our solution, then you can maybe kind of during the degradation process, you lost some of the elements, but but then in our solution you can repair them. What you gain from the solution is the high quality black perovskite powders. So we also kind of we can reuse the solution for quite some time. In our lab we reuse the solution for several months. They are still stable. You can use it many times. Make it very attractive for future practical applications. And after that, we also try to do some life cycle assessment. This is done together with Professor Feng GAO's group at Cornell University. And this is comparison of the 4 spectrum midpoint impact categories. This is comparison. The red ones are from the landfill, and the blue ones are from the recycling. And as you can see here, it's not surprising. By recycling, certainly we can significantly decrease the impacts for all of these different categories. And what's more surprising for us is by the recycling, actually, we can also decrease the levelized cost of electricity. And this was very surprising for our collaborator, Professor Feng GAO, because their group are very good at this different assessment. They are doing this assessment for many different processes, for many different materials, not only for PVs, but quite often recycling is very beneficial for the resource point of view, but not beneficial for the cost of for the cost consideration. Quite often by recycling, actually you increase the cost. But in our case, by the recycling, actually we decrease the cost. That's because in our process we use really low cost materials. We mostly use water, and also we don't involve any high energy processing. We just use a little bit kind of high temperature, 90 degrees, to dissolve the perovskites. So with all of this, so now we think we have reached this kind of vision or ambition, which is the starting point of our project. And through this process, we're using green solvents. I now would like to switch from solar cells to LEDs. But how do we connect these 2 devices? There is a very famous quote from Professor Yablonowicz at Berkeley, which I really like. And I have been very much inspired by this quote: "A great solar cell must be a great LED." For perovskite solar cells, we know they are great, so we can use them for very efficient, very efficient perovskite LEDs. We using the material perovskite for very good perovskite LEDs. But so we spent in the past maybe 1 decade, we spent a lot of efforts to optimize the perovskite LEDs carrying different wavelengths. After we have high efficiency perovskite LEDs, I started to ask myself a question. What's unique with perovskite LEDs? So we have organic LEDs, which nowadays we are using a lot for our smartphones. We also have emerging quantum dot LEDs. Some of the companies, they are trying to commercialize that. How the perovskite LEDs can compete with these other LEDs, organics, QDs. Then we need to think of what's unique with them. In order to answer this question, so I would like to show the history of our mobile phones. 1980s, this is the first generation. This kind of bulky and very small screen. And nowadays, we have smartphones. The screen is very large, almost the same size of your smartphones. You can do many different things through your smartphones. Suddenly, during the past several decades, there are many developments which push this process, hardware, software, many developments. But one development I would like to highlight is a screen, because no matter kind of how many changes the companies are making within the smartphones, as users maybe we don't realize them, but the screen is the interface we as users to interact with our smartphones. So you touch your screen, you read things, and you are using your smartphone, you are using your screens a lot. So display is very important. If we think about state-of-the-art display technologies, the liquid crystal display is still the kind of mainstream, kind of mainly used for TVs. We also have organic LEDs, as I mentioned, and the emerging QD LEDs. Then I would like to ask a question. For these different technologies, which of them can respond to light? For these different displays, which of them can respond to light? Maybe you kind of you're curious. So displays, we provide electricity, we get a light. So why do we care about whether they can respond to light? By response to light, I mean you provide a light to your screen, and then the screen can generate some electricity. But before I answer this question, I would like to discuss with you kind of whether some of them can respond to light. Liquid crystal display, they have no photo response. And organic LEDs, they have very poor photo response because the organic materials have a very high external band energy, and also in this case, organic LED case, we use the planar structure, so the extons wouldn't be easily split into free carriers. For the quantum dot LEDs, the charge transport is not good because of the ligands, isolating ligands, and also depending on the size of the quantum dots, the external band energy can also be very high. So none of them really respond to light very well. But then back to my question, so why do we care about the photo response for displays? So maybe you can take 10 seconds to think about it. So now I will discuss the answers with you. There are good reasons for that. Nowadays, if you take out your smartphone, the screen is not only a display screen. Actually, you also have a touch screen. And you not only have these two screens, you also have a lot of different sensors. When you look at your smartphone in this room, the brightness is not so high. But if you go out in a very sunny day, and you will realize, okay, your smartphones automatically increase the brightness of your screen. That's because we have an ambient light sensor, which can automatically detect the light intensity of the environment. So so that your smartphones can automatically adjust the brightness of your screen. And then you can unlock your smartphones using your fingerprint, because we also have a fingerprint sensor. If we have an LED which can respond to light very efficiently, we don't need a touch screen. We don't need these additional sensors. We only use the LED screen. We can fulfill all of these functions. We can have all of these functions. I will explain to you how that will work. But this is not something new. If we look at the patent, there are already kind of patents on this topic more than 1 decade ago. But in reality, it's not easy to develop this kind of LED. There are quite some efforts in the community using different materials to develop light responsive LEDs, but there hasn't been too many progress. And this is also very much needed by industry. So in the end, the industry they took a different approach. This is kind of product released by Tianma in 2020. In this case, they have this multi-point fingerprint recognition of the liquid crystal display. And so quite often nowadays, when you use a smartphone, it's only kind of one particular place you can unlock your smartphone using the fingerprint. But in some situations, you might need a multi-point fingerprint. For example, if you have a joint account with your partner, and then you need to kind of transfer some money to someone else, and this requires kind of consent from both of you, and then you need to unlock it from both of you. And for some other examples, for example, if you wanted to kind of lock your particular app, but nowadays it's not easy, right? You unlock your smartphone and you give it to your kids, and your kids can play with different apps. But in principle, maybe you wanted to unlock some kind of important apps so that your kids cannot access them. And that requires this multi-point fingerprint recognition. This is something released by Samsung in 2023. In this case, they don't use the liquid crystal display. They use the organic LED display. They integrated the fingerprint sensor and the PPG also on the TFT backplane. This is very similar to what Tianma released, but for different applications. So there is a strong need in the industry, and then if we have this kind of light response of LEDs, then we don't need to have this complicated sensor integration into the TFT backplane. But over kind of more than 10 years, the community hasn't really developed this kind of light responsive LEDs. So we are wondering, okay, are they possible at all? And I don't think there are kind of any intrinsic limitations. The light absorption and the light emission are two very fundamental properties of semiconductors. And as long as we can have the light absorption and the light emission within the same device structure, and then we can have this light responsive LEDs. But that's not kind of, but certainly we need to make them efficient, right? And that's not easy because they have very strict requirements on the materials. These materials need to have a large light absorption coefficient. They also need to have very excellent emission and also excellent charge transport. And also the light emission and the light detection, they should be within the same device structure. We shouldn't kind of using different structure for that. Otherwise, that wouldn't work. And fortunately, perovskite is the material which fulfills all of the requirements. And with that, so I will show you how we make this multifunctional display using the perovskite LEDs. Only using perovskite LED, we can have all of these different functions. And first of all, I will show you the display function. This is certainly required for any displays, and this is also not easy, not difficult for perovskite. for perovskite. This is kind of dynamic display. Maybe you can comment. The resolution is not really good. Indeed, it wasn't good. That's not because of the perovskites. That's because in my group, we are not so good at device engineering. So we also haven't really spent too many efforts to optimize the performance. And I will convince you, perovskites, so they can have very high resolution for LEDs. This is another work we collaborated with Professor Dai Liang's group at Zhejiang University. And they are very good at devices and materials. You can see here, in this case, it's a very high resolution and also very good response speed. In our case, we really wanted to make use of the perovskite LEDs for some new functions. Here, I would like to explain to you this on-screen scanning function. So, for example, you draw a nice picture and you want to scan it. Nowadays, you need to go to a scanner. But if you have a screen which is made of perovskite LEDs, you don't need to go to a scanner. You just put your finger, the figure on the surface of your screen. Then the screen can automatically scan it. That's the reason is. So each and every pixel can work as LED and can also work as a detector. And for example, in this case, this is a LED. The neighboring one is a detector. The reflected light will be detected by the neighboring pixel. And if we scan it, and then so that we can detect the nice heart here. This is what we detected. And very similarly, it can scan the picture. Certainly, they can also scan the fingerprint. In this case, it's not a real fingerprint. We print a fingerprint and then we scan it. The reason still is because the resolution of our LED is not good. If we increase the resolution, then we can kind of scan our fingerprint so that we can have a multi-point fingerprint recognition using our perovskite LEDs without using kind of any additional sensors. This is kind of, this is I think also something unique to perovskite LEDs. Again, here is only perovskite LED. There's no touch screen, but then we can have the function of the touch screen. As you can see here, now it's displayed the two numbers, 1 and 2. And if you move your finger to it, the display can sense it. Then we can have the touch screen function only using the perovskite LED. Certainly, perovskite LEDs, they can also harvest the light. This is we connected the perovskite LED to a supercapacitor, and the red one, the left one is a charging curve, and then we can use the electricity to power our perovskite LED. The same perovskite LED on the right, we just expose it to the light, and on the right, we just using the energy to power the perovskite LEDs. You can see the red curve is a discharging curve. And after we published this article, it generated a lot of interest. Actually, a lot of interest from the general public. There's a journalist from the BBC. He was very much interested in our work, and he interviewed me and wrote a very nice article. I like the screen. I like the title. And he said, okay, the screen tech that can do almost anything. And the kind of at the bottom it says, okay, it looks like kind of relics from the 1980s, but that might represent the future of our display technologies. And this is kind of a visible light. And if we move to the kind of near-infrared light, and we can do something else. For example, we can use it to sense our heart pulse. And you can see here, it's kind of the same device. We have 2 pixels. And we apply positive bias to this device, to this pixel, and negative bias to this pixel. And this is LED, and this is a detector. And the light from this pixel can penetrate into our finger. Some of them are absorbed. Some of the light is reflected and detected by this pixel. So here, this is a finger which is registered on this device. And there's another finger. On this finger, we put 2 commercial devices, one LED and one detector. And you can see that I can show you the video. You can see these two curves. The same curve. Certainly, it's the same curve. It's the kind of they are same because they're from the same person. And if we move the finger away from a perovskite device, and one of the signals is gone. Put it back, and the signal is getting back. And we can also use them for kind of bi-directional communications. I will explain through a video. So in this case, we have two. It's a bit small here. There are two devices. There are two identical devices. The enlarged image is here. There are two identical devices, and this device is connected to this computer, and this device is connected to this computer. And we can use this computer to input signal and this computer to receive signal. And we can also use this computer to input signal and this one to receive signal. I will show you how it works. Maybe the camera text is a bit small, but you can see some things happening from the left to the right or from the right to the left. And if we use a paper to block the path between the two devices, certainly the signal will be gone. And now we have the perovskite LEDs, which seem to be have some uniqueness and hopefully can be promising for some new applications. And they will also need to take life cycle assessment into the consideration. We want to make sure the technologies we are developing, they are sustainable. So we perform the environmental impacts. We also perform the techno-economic assessment. And the results tell us, from the environmental impacts point of view, they are very similar to organic LEDs we are nowadays using from our smartphones. From the technical economic assessment, the price will not be higher compared with organic LEDs if we can commercialize them in the future. And certainly, we need to reach some kind of lifetime to make this happen. And our assessment is that these perovskite LEDs need to reach the lifetime of around on the order of 10,000 hours to really kind of to really make them sustainable. And this is kind of this part is in collaboration with Professor Li Jiashu from Shanghai University and also Professor Olaf Helm at our university. So this assessment really tells us perovskite LEDs are not only kind of interesting and promising from the technology point of view, but might be also very promising from the sustainability point of view. With that, I would like to thank all of my colleagues at Linkoping, my colleagues and team members, and also a lot of collaborators at different places who help us to understand our materials, understand our devices, for a lot of very nice discussions and collaborations. And certainly all of the funding agencies for the financial support. With that, I would be happy to take any questions you guys might have. Thank you very much.